So this presentation, as I mentioned, is the never-ending arms race of FRC. Now, that dramatic title comes from the idea that throughout the history of FRC, people have been looking to iterate drivetrains as much as possible. This comes from the days where people had to make their own wheels and you couldn't buy any online, to today when there's lots of custom pre-made parts that you can get off the shelf from companies. So people have always been trying to push the envelope for drivetrains. And while many teams have always reverted back to keep it simple and make sure it works. So a bit about me, I'm a sophomore here at Northeastern University. This is my second year as a Neutrons mentor, and I was a student on first team 54-59 when I was in high school. It's the Tigers, and the grainy picture in the top right of the screen was my senior year robot, which is my baby. And I'm a mechanical engineering major with a minor in robotics. So as many of you, I'm sure, understand, a drivetrain is the robotic system. It's the locomotive system of your robot. It's the motors, the gears, the wheels, and everything that holds them together that serves as the basis for your robot that moves it around the field. I forget who said this, so admittedly this is a paraphrase of someone's quote, but your drivetrain is your first, second, and third most important mechanism on your robot. I say this because you can design anything you want on top of your drivetrain, and if your drivetrain doesn't move, your robot doesn't do anything, right? So it's essential that your drivetrain on your robot is going to work 100% of the time and is going to be able to function to allow you to do what you designed your robot to do on the field. So when you're designing a drivetrain, there are a few factors that are important to keep in mind. Now, there are more than these that are smaller factors, but these are the big points that I'm going to touch on today, that each of these decisions you make in your drivetrain are going to affect. A big one is agility. How are you moving around the field? How are you able to avoid defense, avoid getting pinned? Terrain maneuverability is one that's big for games like 2016 with Stronghold, where you have to get over obstacles, while there are a lot of games that are flat fields that you can design a really low clearance robot for. You don't have to worry about maneuverability. Rotation point is surprisingly a very large factor when designing a drivetrain. That is, how are you setting up your wheels in the way that it changes what point you're rotating around? That affects the way that your manipulators are able to move towards objects, the ways that you're able to avoid being pinned by defensive robots, and most importantly, the way that your robot is going to be able to be driven for your driver to line up to objectives. Where your rotation point is changes how your driver has to react for lining up any sort of game piece to the scoring position. Simplicity is another fairly obvious one that might go overlooked by a lot of teams. Your drivetrain has to work. It has to not break. That's a big thing with getting picked for eliminations. If your drivetrain's working every match for a district event and it's consistently driving and not breaking down, that can get you on an alliance with a team. Obviously, you want to design a drivetrain that has a low center of gravity so that you're not tipping over, and you want to design it relatively light in general so that you don't go over the weight limit for your robot. And then all of this ties into an ease of driving, because ultimately your driver is the most important person to satisfy when it comes to designing your drivetrain. If your driver doesn't like the drivetrain, then you're probably not going to have a great time with them trying to drive it. So to cover a few of the components here, I'm going to start with wheels. So you have a couple options in terms of wheels and the customizability that you have for these wheels. The standard is traction wheels, otherwise known as just hard rubber wheels. You can see the picture of the Coulsons, top left of all those pictures, are my personal favorite, and the Vex Pro Plaction wheels are right below that. Those are just regular traction wheels. They are relatively simple in concept. I'm sure you understand what they're all about. But then you get to some funkier wheels like Omni wheels, which is the bottom right photo in relativity to the other ones. And those have passive rollers on the diameter of the wheel. What that allows you to do is it allows them to actually roll sideways passively. I say passively because you can't put these on a robot and try to power them to push your robot sideways. But what you can do is put them on your robot, and when you spin, they'll passively glide to the side. So you can use them to change where your robot rotates around because they don't add any resistance to your turning motion. You have pneumatic wheels, which are in the top right corner there. Those are air-filled wheels, is what pneumatic means, and those are used to absorb impact. 2016, as I mentioned, where you had obstacles to get over, sticking pneumatic wheels on your drivetrain is the most effective way, in my opinion, to do that. You have cars, you have wheelbarrows, anything like that typically have pneumatic wheels because they're going over bumpy terrain, and it helps absorb that without having like a suspension system on your robot. And then, I forgot to mention on this slide, but mechanism wheels are the bottom photo there. Those allow you to, those, unlike the Omni wheels, those have rollers along the outside, but because they're at 45-degree angles, with the proper programming, you can run them in directions relative to each other that will actually power your robot to strafe to the side or to one side or the other, as well as being able to drive forward, backwards, and spin like you would with a tank drivetrain. Then within each of these wheels, you can customize the size. Typically, a larger wheel will get you over a larger obstacle, but for a flat field game, you have to realize that when you have a motor, that motor has an output speed, and you want your wheel to spin at a slower speed than your motor is spinning, which is thousands of RPMs, right? So you have to use gears to reduce the speed of said motor to get the speed that you want for your wheel. If you have a larger wheel, it means that the outside of that wheel, for a given RPM of that wheel, the outside point of that wheel, because the circumference is bigger, is going to be moving a lot faster. So you're going to have to put more weight into reducing in your gearbox in order to get your wheels to run at the right speed if you use a larger wheel, which is why typically for flat field games where you don't have to get over obstacles, teams designed for 4-inch wheels or 3.5-inch wheels are relatively standard for that kind of drivetrain. It allows you a lower clearance, a lower center of gravity, and a lot less of a reduction in your gearbox. To power your wheels, you have motors. I mentioned these spin at thousands of RPMs. You plug them into a gearbox, get the motion of your wheels. The three main types of motors you'll see in FRC drivetrains are Sims, Mini Sims, and 775s. The Sims are the image on the left. The image on the bottom is actually a bag motor. That should be a Mini Sim. And the top right is a 775. For those of you who are curious, your Sims are your standard in FRC, as you might imagine. They're durable. They're not going to fry out on you. And if you use 2 or 3 of those per side of your drivetrain, you're pretty set for a reliability standpoint. Both Mini Sims and 775s have been introduced into FRC for drivetrain purposes only recently. Both of those have been used in manipulators more commonly, but because extensive testing hadn't been done with them yet on drivetrains, not many teams use them. I'll get a little bit more into that later in the presentation. So when you're selecting a motor, you have motor curves. VexPro, which is a company that makes commercial off-the-shelf parts for FRC, has specs for each of the motors that they sell, and many of them look like the image shown to the right side of the screen. The idea behind selecting a motor and selecting which output speed you're looking for on your motor is to look at the peak power that the motors are sending to your drivetrain. That's the most important part of any of this. If you see the green curve here, as the motor increases its RPM, it increases the power that it's sending to it, but the power actually decreases at the higher output speeds. So while a motor might be spec'd for a really high output speed, what you really want to be running your motor at in terms of the software is at that peak power point, which here happens to be at 2,670 RPMs. So if you have two motors on each side of your drivetrain, that gives you, in this case, this is a sim motor, so that'll give you 337 watts times however many of these motors you have on your drivetrain. You run them at that RPM, and then you use gears in order to get that RPM down to the RPM that you want your wheels to be running at. The basic idea behind that, which I don't go deep into in this presentation, is that if you have a gear that's twice as big as the gear that it's meshing with, you're having the speed, but you're multiplying the torque, which is the rotational force that it's delivering, by 2. So you use multiple stages of gears in order to cut down that speed to the right amount that you want. If anyone has any specific questions about that, I can go more into depth about that at the end. You can do this sort of power transfer typically through gears, as I mentioned, but you can also use belts or chain in order to transfer this power from your motors to your wheels. Typically what people will have are a gear reduction from their motors to one wheel, and then you'll use belts or chains in order to transfer that power at a 1-to-1 ratio to your other wheels on your drivetrain. So belts are typically lighter, but they're newer in FRC. Not as many teams have used them yet. And you have to design them into CAD because you have a very fixed length belt, and you have to design the spacing between your wheels to be appropriate for that spacing for that length of the belt. Whereas with chain, even though it has more weight to it, you can make it any length up to plus or minus one length of a chain, which is it's probably around a centimeter for one length of chain. So there's more adaptability there. You don't necessarily have to plan for an exact length of chain. You can design your drivetrain and then attach the chain and trust that it'll be within tension relative enough. We used chain on our robot last year for that purpose, and it worked great for us. And then if any of you have heard of direct drive, it's just using the motor on the wheel and just running it. And that's a really bad idea because now your wheel is starting to run at the max speed of your motor, which it sounds obvious not to do, but my rookie year in FRC, that's what we did. So I'm just stressing this now. You want a gearbox to go to your wheels. So most of the rest of my presentation is going to be based on the types of drivetrains. I know I've been talking about the components, but this will hopefully contextualize all of it for each of you in terms of how does this all come together and influence the type of drivetrain that you try to design. These are archetypes, as you could say, within FRC of what most teams do. Not necessarily everything that's possible to do, but everything that you would likely consider during an average season. So the macro perspective of drivetrains are you have tank drive, holonomic drive, and then what I'm categorizing as exotic drives. The idea behind it is tank drives are the most straightforward, most classic design of drivetrains. That's the type of drivetrain that you'll get in your kit of parts if you're using the kit of parts drivetrain, and it's the most likely to be robust and to work. Holonomic drivetrains are similar to tank drivetrains, but will allow you to move in directions that aren't just forward, backward spin. You could also move side to side with these drivetrains. And then exotic drives are what I'm categorizing as anything that isn't a tank or holonomic drive. This is typically a combination of the two or of any funky designs that anyone's ever come up with. So, oh yeah, I got some pictures here. Tank drive, holonomic drive, you can see them labeled. I'll go more into depth with each of these categories in a second. So tank drive, I think I relatively explained before, but the idea behind it is that similarly to a tank, but without the treads, you have two sides of your drivetrain, and you have 3 or 4 wheels or however many on each side of those drivetrain. And the two sides of the drivetrain are powered independently of each other, but all of the wheels on each side of the drivetrain are powered together. So the idea is you have 2 or 3 motors power each side of the drivetrain. If you power both of the sides of the drivetrain forwards, your robot will go forwards. if you put them both in the backwards direction, your robot will drive backwards. But if you drive either side in opposite directions, it's going to spin your robot in place, right? Any degree in between that, you can, turn. And that's the general idea behind a tank drivetrain. The customization that you can do within this are have typically of traction wheels, but you can use 4, 6, or 8 wheels. You can do what's called a center drop, or put omni wheels in the corner, and then you can swap out any of these traction wheels with any of the wheels I talked about earlier. Now, that doesn't mean anything if I don't go into exactly what these change. So what you can do, right, is if you have a standard 6-wheel traction wheel drivetrain, that's pretty standard in FRC. That's what the kit of parts drivetrain is. That's great, but you can modify them to do, say, you can use omni wheels to change the rotation point of your robot. You see in the top right, there's a picture of what's called a 2+2 drive, where you have 2 traction wheels and 2 omni wheels. Now, typically, your rotation point is going to be right on line in between all of your traction wheels. So if you had all 4 of those wheels as traction wheels, your rotation point would be right in the center of your robot. But because you swapped out those 2 traction wheels with omni wheels, now your rotation point is between only your traction wheels. And you rotate around, in this case, the back of your robot, right? So this can be useful for scenarios where you want to line up to a specific field element, right? And you want to be able to rotate your robot, but every rotation is only going to move, the front of your robot a minimal amount. You don't want that front of your robot whipping around. You want it just to be a precise rotation around the front of your robot. So scenarios like this are pretty common. For those of you who are familiar with 2017 FRC game, Steamworks, a lot of teams who tried to place the gears on the pegs would use a 2+2 drivetrain because they're able to have the gear held in their robot right next to the traction wheels, and the rotation point is very controlled right around where they were trying to line up the gear. It allowed them to control it really well. The other benefit of adding these omni wheels is when you're rotating your robot, any traction wheels that aren't in line with your rotation point are going to create what's called scrub. And what scrub is basically dragging your wheels across the floor. Because if they're not in line with your rotation point, it means they're partially rolling around it, but they're also partially being pushed and forced across the ground around that point, which makes it really hard for robots to turn. Now, while omni wheels, like I said, can passively slide to the side, now with this 2+2 design, your rotation point is now right in line with your only 2 traction wheels, and you're not getting any scrub from your omni wheels. The other way to do this is what's called a center drop, and this is more common in FRC, and that's where you take the center wheels of your drivetrain and you move them down 1/8 of an inch max. You don't want to go up to like 1/4 inch unless you have a very specific reason to. But if you drop those middle wheels, then now when you're accelerating one way, your robot rocks back just a little bit, and the wheels that are in the front won't be touching the ground, and you'll actually just rotate around your back wheels and be riding on those wheels, and you'll get significantly less scrub, as I said. So in the case of a 6-wheel drivetrain, you drop the middle 2 wheels. In the case of an 8-wheel drivetrain, you might drop the middle 4 wheels, or swap out the corner wheels for omnis in this case. Therein lies the big difference typically between 8-wheel and 6-wheel drivetrains. 6-wheel is simpler, it's lighter, it's mechanically less parts, and takes up less space. But like I said, you're only ever riding on 4 wheels, which means that your robot's rocking a little bit back and forth. If you design an 8-wheel drivetrain, then you're allowing yourself to have the middle 4 wheels dropped. And so that way, most of the time when you're driving, except when you're accelerating, you're flat on those 4 wheels and you're not leaned one way or the other. It's particularly useful for games where you're shooting and you need to know that your robot's not going to be at an angle. Steamworks, again, is a great example for this. Teams that didn't use the 2+2 that were shooting typically used an 8-wheel drivetrain as opposed to a 6-wheel drivetrain in order to stay flat on the floor. And then the last customization is changing the number of motors you have. This is based on the power output that you want from your drivetrain. I always like to note the standard is 4 sim motors, 2 on each side, powering your drivetrain. Sometimes teams will do 6 sim motors in total, 3 on each side, which allows you to deliver a higher output power to, I don't like to say pushing robots around because strategically that's not that useful, but in order to prevent getting pushed around by other robots is how I like to put it in that case. My high school team in 2017, like I showed in the first slide, designed a pretty light robot. So we stuck 6 sim motors on it in order to compensate for the lightness of our robot. That way we didn't get pushed around. I have a link to a video here just to kind of show the mechanics of a tank drivetrain. This is our 2014 drivetrain. You can see how it moves. It's pretty zippy because there's no manipulators on it. This slows down a lot once the rest of the robot's on it. Yeah, but that's tank drivetrains. Those are your standard in FRC. Did this just... Oh, there we go. Okay. And these are a very abstract but formulaic concept. You can take a lot of formulas to them to develop what you want, right? I need my rotation point here. I can either do a center drop or I can put omnis there. I need this much power. I add these motors. I need to get over obstacles. I use pneumatic wheels. You can apply each of these formulaic things, but there's definitely some area for creativity with it in design. I mentioned I can talk about that at the end if you'd like. Oh, shifting is a great thing. And last year I talked about that I'll add that in at the end and talk about that for a bit. The general scope of what I have up here is talking about the types of drivetrains, but I'm more than happy to answer any questions about transmissions because shifting drivetrains are an interesting subject that I like to talk about. So then the next option here is if you say you're not satisfied with being able to drive forward, backward, and spin, you want to be able to move to the side while you're moving down the field, a holonomic drivetrain would be the way to go. Now, these are typically your more flashy drivetrains, but are much more complex in terms of their design. The first one that I have here is H-Drive. It's called that because you basically have 5 or sometimes 6 omni wheels set up in an H configuration, as you'll see in the video that I show up. The idea is that your corner wheels are all omnis, and then you have perpendicular wheels in the center of your robot, either 1 or 2, that will push your robot to the side, and that allows you to strafe, as you can see in this video here. Yeah, so that's strafing there. Then you have a simpler construction method called mechanism drive, which is where you use the mechanism wheels I mentioned before with the rollers at 45-degree angles on the outside of them. This is a 4-wheel drive robot. You don't need the wheels in the center, but you're going to lose a lot of traction with both of these methods because they have passive rollers on the outside. So realistically, if you're trying to drive into another robot and they're pushing back on you, then your wheels can be spinning, but the rollers can be spinning just as fast in the other direction, and you can just get pushed. Mechanism drive isn't quite as, it's a little bit more jittery than H-Drive. It's not quite as smooth because each of the rollers are slapping the floor in very subtle ways. You typically get more drifting if you're trying to strafe, or if you're trying to drive forward, you might start to drift to the side with this method. But this, the beginning of the video is the best for this. You drive 2 wheels towards each other, 2 wheels away from each other on either side of the robot, and it'll direct you one way. Flip it, directs you the other way. This is, like I mentioned, an easier system to pull off than H-Drive, but not nearly as smooth. And then my favorite, which I technically should not advise any of you to attempt right away at all, is called the swerve drive, where each of the wheels is a live unit itself, where as opposed to just spinning, it's also pivoting on the vertical axis. And if you program it correctly, it means that you can control your rotation of your robot and the translation of your robot across the ground completely independently of each other and simultaneously with each other. This is a good video by Team 1717 that no longer exists, but they had one of the best swerve drives while they were in FRC. They basically decided to, this was a capstone program at their tech school, and then they replaced it with another capstone program. They were like the only FRC team that's ever outgrown FRC. Like that's ever truly felt like, oh no, we need something more than FRC. But yeah, it's pretty cool what they can do with it. It's extremely complex. I think I have a picture of it on the next slide, but that's Swerve Drive, which is one of my favorites. Yeah, so you saw Mechanism Drive. H Drive is a better example here of being able to actually see it. You have the one wheel in the center that allows you to strafe. You might also see two wheels in the center on a rocker, where each wheel is powered by the gearbox in the center, but depending on which direction you're driving it, it'll slam that rocker into the ground. A big problem with H Drive is that you might not get the right contact on each of the wheels that you want. So that rocker in the middle, right, you're driving to the right side and it'll slam to the right, push that wheel into the ground with the force that you're driving it with. Helps you get traction. And then Swerve Drive, as you can see here, is extremely complicated, where each of these wheels has its own gear reduction in the modules, and each of those modules rotates around the vertical axis. One motor to drive the wheel, one motor to pivot it for each of the four wheels on that robot. I love Swerve Drive, though. And then the last category of drivetrains here are exotic drives. And this is what you define as the arms race of drivetrains, hence the title of the presentation. You know, you'll see a lot of times if you're looking at Chief Delphi or any other online forums, if you're looking at Discord, for those of you who are in the FRC Discord channel, there are people who are going to get bored and design drivetrains or teams that are using it as an off-season project. Typically, these will consist of actuated parts, wheels that are going to move up or move down, or using an absurd number of wheels or an absurd number of motors on the drivetrain, right? I covered the general, you're using 4 wheels or 6 wheels or 8 wheels, but some teams will be like, we're going to design a 15-wheel drivetrain. Those would fit the category in this situation of exotic drivetrains. A few examples of these are any sort of insect/critter drive, which is this drivetrain by Team Spectrum, where you have 2 drivetrains simultaneously, and you drop one down depending on which one you want to use. This one is Butterfly Drive, which, if I remember correctly, I think should be on the next, a picture should be on the next slide. Yeah, which is this in the top left here, where you have traction wheels and omni wheels on each corner of your robot. And if you drop down the traction wheels, right, you might have a 4-wheel traction drive that has a lot of scrub. I would not advise doing 4-wheel traction drive, but they can drop the traction wheels in the back of the robot while keeping the omni wheels in the front of the robot, and they have a 2+2 with the rotation point around the back of their robot. Or they can drop the front traction wheels and have the omni wheels in the back of their robot and rotate around that point of the robot. Or they have the H drive system here, which is the 2-wheel rocker system I was talking about. And if they pull the traction wheels up all together, boom, they have an H drive, right? They have three drivetrains, 2 of which happen to be the same thing in reverse of each other simultaneously. It allows them to do some pretty cool stuff with it. Another one I wanted to mention is Kiwi Drive, which is basically putting 3 omni wheels on the corner of a triangle in your robot at different angles and running them to allow yourself holonomic motion. I typically don't advise using this one, though, because it's really easy to push around and makes your robot a triangle. One team that really did pull it off was Team 1114 Symbotics in 2015, where they did design a almost triangle robot, but used the gap in their robot to suck in the game pieces, which were large totes. It's one of the best design robots of all time, and it used Kiwi Drive. So can't really diss Kiwi Drive if if one of the best robots or one of my favorite robots of all time has it. And then, there are different things like I mentioned, like replacing the sim motors with 775 motors. Some teams will use like 4 775 motors as opposed to 2 or 3 sim motors, which gives you a huge power output into the drivetrain, but they're typically more likely to burn out. When you are driving them into a wall, they'll probably start to burn. But a lot of teams are starting to test them. I mentioned the H drive. Here's 4 775s hooked up to a drivetrain, low profile, small motors, high output, high power output. You have Octacanum, which is a similar concept to H drive, but instead of swapping out a 2+2 for an H drive, you're swapping out a 4-wheel Omni drive for a Mechanism drive. And then there are a bunch of those actuation versions. And then a few versions of Swerve here, which are one team, Conage, I'm forgetting their number at the moment, did a sim in-wheel swerve. So the motor is inside the wheel in a bearing, and this switches differential swerve, which is using both motors, not one motor to drive the wheel and one motor to spin it. It's actually using the difference between the speeds of the two motors to both spin and pivot the wheel. I'm actually working with a group here at Northeastern to design one of these, which is super cool. The big emphasis of this presentation is, as much as I talk and geek out about all of the cool drivetrains, you really need to build to your capabilities. Your drivetrain needs to work, and cooler isn't always the best. A great example of this is the two examples of the different approaches are Team 254, the Cheesy Poofs, and Team 148, the Robo Wranglers. Team 254 consistently builds a tank drivetrain every single year, and it looks very similar every single year, and it works every single year. They design their robot around it. They design most of the time some of the best robots in the world around it. And in their mind, if you're spending any time on your drivetrain that you could have been spending on something else, it's just not smart. Now you have 148, the Robo Wranglers, who take the approach of your drivetrain is another mechanism on your robot. So they go and they redesign their drivetrain basically every year. Every off season, or most off seasons, they'll come out with a new prototype drivetrain that they'll release a white paper on Chief Delphi. But any year they might have an H drive drivetrain, or the next year they might have. I think they had an Octacanum drivetrain one year. You might want to fact check me on that. But they venture out and try different drivetrains every year, and they're always exciting to look at what they do, because they use it, like I said, as a whole subsystem, as another mechanism itself, and really use it to their advantage to play the game in an efficient way. I'm always going to recommend, if you're just starting out with drivetrains, the Kit of Parts chassis up in the top right there. It's a great bet for anyone. It's free with registration, of course, and it's going to work. You're going to be able to assemble it the first week of build season, and you're going to be able to build everything around it and focus on other things. It's great. It's well designed over the years. There was a team 1114 that used to release a packet called Kitbot on steroids that would tell you how to make the most of your Kitbot, but they stopped releasing it mainly because the Kitbot is so developed at this point. There isn't much to do to improve it. So it's a great drivetrain, and you can get it running really early, get your driver starting to work on it really early. If you are looking for a step up in your drivetrain, I would highly recommend the Vex Versa chassis, which is basically using prefabricated tube stock and what are called gussets, which are the little pieces you can see in the corner here that attach each of the tubes, and their gearboxes and wheels in order to build a drivetrain. This is what I did with my high school team for 2017, and it's probably the best decision that we made. It's much easier to attach everything to, and the Vex Versa frame system is a very good universe to design your robot in. Even though it's slightly more expensive than just buying stuff from Home Depot, it's great for a step up, even if you just have a bandsaw and a drill press. You can design a robot with like that robot in the top right was designed, not the one on the top left. That was an experimental thing. Top right, that was designed basically all with a drill press and bandsaw, except for the bucket on the front. But that could have been done the same way. And then, but what I will mention is that in the off season, I think drivetrains are one of the best things to do to try to design. You probably won't want to start with designing an adventurous drivetrain during build season, but it's one of the best learning opportunities you can do to try to design one of the like exotic drivetrains in the build season. Because the worst thing that happens is you don't use it, but you learned how to design it and you got experience from it and you know how to design drivetrains. And it's a really cool experience to try out that kind of stuff. Yeah, so this was in the bottom left here. This was an off-season drivetrain by Team 2363, triple helix. And they just prototyped these drop-down Omni wheels that allow them to make a simulated 2+2 to get out of pins. And it's just a cool project that they put together. I don't think they used it in season, but their students learned a lot from it. If you're looking, I've mentioned a few of these, but if you're looking for ideas or for help, Chief Delphi is the online forum for FRC and is where you'll find a lot of these experimental drivetrains. This is the logo of the team that started Chief Delphi, but you can just Google it and it'll pop up. It's a great resource. Discord, there's an FRC Discord channel. There's also a New England First Discord channel for those of you who use Discord. It's a great way to conversationally interact with people in First. And then, of course, the Compass Alliance, as I hope all of you have heard about today, is 125's collaborative platform, or it's not our platform, but we're a part of working on this platform with a bunch of other teams in FRC. Basically concentrates all the resources that are online from other teams into one place, as well as creating, pathways, which are like a running a team pathway. It's going to take you A to Z on running a team, or a strategic design pathway is going to take you A to Z through that whole process and link you to articles, that way to concentrate your efforts. And that's always a fantastic resource to check out. For parts, you can go to McMastercar, which is like a 2-day turnaround from the time you click order to the time that it's in your mailbox. Is lots of hardware parts. VexPro, which I mentioned, has the whole VersaFrame sub universe of parts. AndyMark is the official vendor for First. They're the ones who sell the field elements and a lot of the wheels and gearboxes you'll find on robots. And then BaneBots is the one over on the right. They sell some planetary gearboxes, some wheels, and other cool parts for your drivetrain. Before I open it up to questions, I know we did have the question about transmissions and shifting gearboxes, which I will address before we get to any other questions. How are we doing for time? Oh, pretty good. 20 minutes left. So for transmissions, I briefly went into this before, but the idea is that you have your motor spinning at an output speed probably around 3,000 RPMs. Now, you don't want your wheels spinning at 3,000 RPMs, because not only would that make your robot theoretically go really fast, but the robot won't actually go in that you're going to burn out your motors. It's not going to work. So what you want is to design what's called a gearbox to reduce the speed of the output of your motor to the speed that you want your wheels to be running at. What this also does in turn is increase the torque that the motors are sending to the wheels. Again, this is the rotational force of what the wheels are outputting to the ground. It's basically the force that the wheels are putting on the ground multiplied by the radius of the wheel. That's what's called your torque. So the idea behind that, go back to motor curve slide. Okay. The idea is you select a motor based on the output power. For a certain load, for the certain weight of your robot, the acceleration that you want to achieve and the top speed that you want your robot to go at, you're going to need a certain output power in order to achieve that. So you add the specific amount of motors that achieve that output power, and then you use this peak power on the curve here, and that's going to give you, for a sim motor, 2,670 RPMs that you want to be running the output of the sim motor at. But you don't want your wheel running at that. So you use gears in order to reduce the speed of your motor to the speed you want your wheel at. Who here is familiar with gears in general? Like, I'm sure you've all heard of what gears are. The idea is, as I briefly mentioned before, the ratio of the diameter of the gears is going to reduce the speed of your axle, of the next axle, proportionately. So if you have a gear that's 3 times the size of the gear that it's spinning, then the gear that it's spinning is going to be, no, I said that wrong. If you have a gear that's 1/3 of the size, that's an important correction. If a gear that's 1/3 of the size of the gear that it's spinning, then the gear that it's spinning is going to be running at a 1/3 of the speed rotationally. And then if you take that shaft that you just made spin slower and you put a small gear on that shaft that goes to a larger gear on the next shaft, then you're reducing the speed proportionally even more. And the idea is, through typically 2, maybe 3 stages of this, you can reduce the speed of your gearbox down to the speed that you want your wheel to be running at, based on the top speed of your robot and the acceleration that you're looking for. A great tool for this, there's something called the JVN Design Calculator. JVN is a mentor for Team 148, the team that I mentioned that likes to make cool drivetrains. And he basically released this spreadsheet that will do most of the calculations for you if you input what you want your top speed to be, and what motors you're using on the drivetrain. So if you do that, you can play around with, if I use a 13-tooth gear to a 24-tooth gear, and then a 20-tooth gear to a 36-tooth gear, what output speed will this give me on my wheel? You can put all that stuff in, and it's really particularly helpful for designing your drivetrain effectively. To talk about shifting gearboxes, who here has heard about shifting gearboxes? Okay, so when you're looking at a car, right, you have different speeds. Obviously, most cars nowadays are automatics, but you guys are familiar with manual cars, right? Shift into gear, shift into the next gear, right? The lower gears give you more acceleration, but they have a lower top speed. The idea behind that is that you have your lower gear ratio, your speed 1, is going to give you a lot of torque. It's going to be a much lower speed gear ratio, but because it's targeted for a lower max speed, you're going to be able to get to that max speed a lot quicker. And then when you're close to that max speed, you shift into the second gear to allow yourself to continue to go higher at a slightly slower acceleration. Now, some teams will use a 2-speed gearbox in FRC. And you typically use what's called a pneumatic cylinder, which uses air to actuate a rod back and forth. You can use a pneumatic cylinder to engage or disengage the last stage of your gearbox. So you basically have 2 gearboxes in one, and then on your last axle, your gears are on bearings as opposed to being attached to the axle, and you use what's called a dog gear to slam into the gears to engage them to make the output shaft spin at the said speed. It's a bit of a tricky concept to grasp, and I'd be happy to explain it more to anyone later, but I won't get too far into that. In terms of my recommendations for that kind of gearbox, in FRC, your acceleration profiles are pretty quick. So it's typically not very useful to have a 2-speed gearbox to help you accelerate to max speed quicker. Some teams have used it. I wouldn't suggest it to most teams for most years. What I would suggest using a 2-speed gearbox for is if you want a robot that's capable of operating at 2 speeds separately entirely. So this would be, you'd use 1 speed to drive down the field, and then a lower speed to line up to the game element. A good example of this is Team 5687, the Outliers, who in 2017 built a robot that did the game objective that was scoring the yellow gears. For those of you who are familiar with it, they are one of the best at it in the world. They basically had a 2-speed drivetrain and a really light robot that sprinted down the field to get the game piece, sprinted all the way back. But then when they were lining up, they went to their lower speed, so they had more fine-tuning adjustment when they were trying to place the piece precisely. That would be typically how I'd advise using it. The other approach is if you want a really fast robot, but you don't want to get pushed around. That might be a method, but typically when you're looking at robots, if you have one that's like going 14 feet per second, you're pretty set for most games. You don't really need a robot that can go like 18 feet per second and 9 feet per second. It's helpful, but it's not necessary for like most scenarios. Are there any other questions? Yeah, Patrick. Oh, you want to go into flipped gearboxes? Okay. Flipped gearboxes, well, that's only applicable if you're really designing your own gearbox, though I know that a company called West Coast Products, which is in association with VEX, has started to sell these. The idea is that when you have your motors going into a gearbox, you have your motors here, you have your gearbox in front of those, and then in front of those, you have your wheel, right? There's 3 stages. If you take those motors and you put them on top of the wheel, and then you have the motors going into the gearbox, and then the gearbox output shaft goes in the other direction, you can have the motors over the wheel. It takes up less space horizontally in your robot. Typically, it's much more compact, and you're putting more weight concentrated above your wheel, which is going to give you more traction. That's more over something that you'll see when you're designing like a custom gearbox, which is one of the last things you're looking to do custom on your robot. Because you can get some great off-the-shelf gearboxes from Andy Mark and from VEX Pro, but I think they now offer a commercial off-the-shelf one. Are there any other questions about like the types of drivetrains, ways you might change out components in order to design an effective drivetrain, number of motors? I kind of whipped over a lot of the tank drive stuff, but there's a lot of configuration stuff there. No. Oh, got a question right here. Special wheel substitutions. Left middle are Plaction wheels. They're traction wheels with Plaction. Oh, not Plaction. Sorry. They're typically plastic cord wheels. So the rim per se of the wheel is plastic, and then you'll have a rubber tread on the outside. That's actually the brand name for them. It's not the actual Plaction's VEX Pros, or I think Andy Mark might use it as well. It's just that type of wheel. That's a great question. I always love Coulson's, which are top left. That's what we used last year on a robot. Highly would recommend. Really quick, really easy. Usually have a hex hub in the center, so you just put them right on a hex axle as opposed to having to stick your own hub onto the wheel. Really easy, reliable, don't wear down that fast. Regulation around what? You can use theoretically any size wheel that fits within the total frame of the robot. I wouldn't recommend using a giant wheel. Your range of wheels are typically going to be, that's a good question, the range of wheels. You probably won't find any wheels under 3 1/4 inches unless you're us at the end of the season. Once they've really worn out, then there'll be a lot less than that. 4-inch wheels is typically the standard. And then for games where you need more clearance, you're going to find 6-inch and 8-inch wheels more commonly. You won't really find anything larger than 8-inch wheels. 8-inch pneumatic wheels, as in the top right picture here, are the most common to find for a game such as Stronghold in 2016, where you have to get over obstacles because they have the biggest clearance over the obstacles and give you some bounce. We used 5-inch wheels this year on our robot, which is a rare thing for us to use 5-inch wheels, but we just had to have clearance over one of the platforms on the field, and 4-inch wheels weren't enough to give us the right clearance. And we didn't want to have to use the 6-inch wheels because then we'd have to have a larger gear reduction. So we used 5-inch wheels. That was sort of a niche scenario. Oh, yeah.
So you said something about like when you were making your robot for the first time, like you put a motor to the wheels. What did you mean?
Oh, actually, I should start repeating the questions for the audio in case it's not picking up from the audience. So the question is, when I said I put the motor right on the wheel, what did I mean? It's a slightly embarrassing story of a team that didn't attend a university day like this and didn't learn this stuff, where instead of having the motor attached to a gear, which attached to a gear and a gear and a gear, right, and having the gearbox to reduce the speed of the motor to the output of the wheel, we hooked the motor directly to the wheel. So the motor was trying to spin the wheel at thousands of RPMs, which for many reasons is bad for the motor, bad for the wheel, and just not a great scenario. Though you would be surprised how much, you might not understand that needs to be done. If you're someone who's done like a robotics like class, but like in school, you're typically not worried about gear reductions because you're using like hobby motors that are spinning at a much lower RPM and are designed that kids can just hook them right up to the system and don't have to worry about the speed that they're running at. And that's sort of where that resulted from, and the reason why I emphasize it so much in my presentation. We have 5 minutes left if anybody has any other questions. Otherwise, we can call it a day. Yeah, thank you.